effects of electrostatic electricity have been recorded since 600 BC, when the ancient Greeks realized that tiny fibers were sticking to the tree sap. In today's world, electrostatic electricity has many applications and can be seen in many different ways. From the production of electricity that is used in homes to lighting, electrostatic electricity plays a large role in today's society. Perhaps you have noticed electrostatic electricity after getting out of your car. You touch the door to close it and you get an electric shock. This is due to the static electricity that has built up on your car's exterior from contact with the wind. Every atom contains some sort of electric charge. Whether it is the positive or negative depends on the amount of electrons and protons it has. If an atom has an equal amount of protons and electrons, then it is positively charged. If it gains an additional electron, then it is negatively charged. This is known as a cation. If it loses an electron, then it is positively charged. This is known as an anion. However, protons and neutrons have the same magnitude, as well as neutrons not having any charge at all. The transfer of electrons is generally caused by friction and the contact of two materials. So now we know the basics of how the atom works with electrostatic electricity. Let's learn how that works in practice. Two positive charges will repel each other, and two negative charges will also do the same. However, if we have a positive and a negative, they will attract and pull each other together. As the rule goes, opposites attract. Now let's look at a quick example from fun science demos.
I have this material here, it's wool, and I have my balloon, and now I'm going to rub off my negative charge. I'm rubbing it off. You can't see it, I can't see it, but I'm rubbing off the negative charge here. Now, I rubbed off the negative charge and I have the negative charge on this balloon. And I have the positive charges on these pieces of paper, these little guys. Let's see if they can attract. Woo, they're jumping on. They're jumping off.
But how do we measure this, and how do we measure the strength of these electric fields? Well, electric charges are measured in a unit called a coulomb. A coulomb is equal to the amount of electricity transported in 1 second by one current of 1 amp. Electric fields have a charge and a direction. Every single one has. The direction of an electric field can be found at a specific point using only a very small charge, which is known as a test charge. This charge is simply used to find out whether the charge will be pulled in or pushed away from the field. This charge simply illustrates whether the charge is being pushed or pulled away. If it's getting pushed away, then that means the field is negatively charged. But if it is being pulled in, this means the field is positively charged. The strength of an electric field can be defined and expressed in an equation. The electric field is a field of force, and this is something that is important to remember when talking about electric fields. In this equation, E is the electric field vector, F is the force on a small test charge, and Q is the strength of the test charge. The electric current is the rate at which charge flows, whether it be in coulombs, seconds, or amps, under the influence of an electric field. Now, electric current can be in either DC or AC. DC forces the current to move in only one direction, while AC moves it to move back and forth periodically. This means that we can have positive and negative charges moving forwards and backwards through a series or parallel circuit. Now we know what electrostatic charges are and how to work with them, we can do some questions to solidify our knowledge and test what we learnt. Here's an example question. What is the electric field if a charge of plus 6 Nc placed at that point in the field experiences a force of 2.5 times 10 to the power of minus 6 N? Well, using this equation, E equals F over Q, we just simply substitute these numbers in. First of all, however, we have to change the nanocoulombs into coulombs. And this is just simply 2.5 times 10 to the power of negative 6. And Q remains the same. Remember, Q is the force of the test charge. So E equals F over Q. So this will be 2.5 times 10 to the power of negative 6, over 6 times 10 to the power of negative 9. And you'll find that the answer you get to that is 416.67. Thanks for watching the video, and I hope you learned something.